Okay, so we've got our data pulled up. We've changed our labels to look like what the name of the variable is. We can flip back over to data view or not. It doesn't matter. But let's do a regression model. We're going to go analyze regression linear. Actually, before that, let's go descriptive statistics, or I mean, correlate bivariate. Let's remove this. We don't need mindful in there either. DIRS, alls, DTS, AIM. Yeah, let's look at all of these. If you go under options, and don't worry about it, and hit go, and here we just have our basic zero order correlations amongst DIRS, which stands for difficulties in emotion regulation, alls, which is affect lability or emotional instability. Most of this stuff is going to be tied to emotion in one way or another. DTS, which is distress tolerance, your ability to kind of tolerate negative emotion. And then AIM is affect intensity. That means how strongly you feel emotions when you experience them. So they're all kind of different aspects of emotional functioning. And so we are going to test something here. Let's go analyze regression linear. In the video that I gave you guys, yep, we're going to have DTS in there. I'm going to do something here real quick just to make sure that we're all on the same page. Do I have anything else? No. Okay. In the video that I gave, when we were talking about ways to show causality, the video talks about 4 different ways to show causality. What is the first way that we show causality? Temporal precedence, right? Something happens and then something else happens. What is the second way that we can show causality? So that's the fourth way, and the most important way.
That's why.
The second way is that when you manipulate X, that it causes a subsequent change in Y, right? So some sort of a manipulation shows that you can cause that change. Although that's not necessarily true. The third way is what? You manipulate X, it causes a change in some other variable, which causes a change in Y, right? We have some sort of intervening or third variable. And then the last one is that the way that we can roughly show causality is that there's some sort of sound theoretical rationale for why this might be occurring. Okay, we're going to look at one of those latter examples today, the theory-driven way. In every single one of these, though, they should be theory-driven in some way, right? I mean, even the experimental manipulation and so on should be theory-driven. But all right, we're going to look at distress tolerance, and we're going to see if we can predict distress tolerance by 2 of these different variables. First, we're going to look at affect lability. Does your level of affect lability influence how much distress tolerance you have? And let's look at difficult. Oh, click next. I'm sorry, mine's not going to next for some reason. Then next. Why is it not working? I hate SPSS so much. Let's see if this just runs just like this. It did. Analyze, regression, linear. That's interesting. My alls has like disappeared from here. Alls. You're bugging me. And the blocks aren't changing either. What the hell? Okay, you know what? I'm going to just shut this down and restart my SPSS. I wonder if it's... Oh, wait. Cancel. Analyze. Let's try it in this box. linear. Is this the same box I just had open? It probably is. Of course. Save changes. No. All right. No. Yes. Who are my Office fans again? Who was it last week that like? Oh wait, maybe that was in lab meeting, wasn't it? Yeah, yeah. So there's this. Okay. No, it's like completely locked.
Is that your citrus?
It is. No, it shouldn't have. Yeah, that's. So this is working. It appears to be working.
Just started to go funny. Like mouth breathing.
Can I just close Citrix Viewer? Disconnect. Oh, I wonder if I have to relog in though. Do you think if I hit refresh, it seemed to work? I don't know.
Also, your laptop.
Thank you, Moses, for showing off your laptop case.
Cute. Amazon for like $7.
So cute.
I don't think it protects anything, but
But
it was cute. Yeah.
Yes.
That's all. Like, I never watched. Are we supposed to wash our laptop cases? Like, my thing's old and probably really old.
No, like it's so old and so good.
Huh?
You're like, the thing is, I don't know.
Are we supposed to?
I don't know.
I wipe mine down every once in a while.
You know,
But
like bad
because I eat it.
Like neoprene or whatever?
I never washed it.
Oh, this one's so dirty. It has
Is it like
stuff on it.
wash or save?
I don't know.
I think so.
I just thought of that the other day. Sorry.
I should wash mine.
Maybe hand wash it.
Hand wash line.
There you go. Comes like right low.
Maybe I can wash it.
Okay, we're back. Let's try this again. So if we go analyze, if it doesn't work this time, I'm going to flip out. Regression, DTS. Then we're going to put alls in here in our block 1. Ah. DIRs in block 2. Let's go to statistics. Let's get our R-squared change, and let's get our part and partial correlations. Now somebody else's is not working?
Yeah, mine just completely now. Must have just, decided to.
Is it doing the same thing as mine?
No, it's just that the arrow thing. Well, yeah, it's just the arrow thing and the next thing.
Okay. Well, restart yours and just follow along. All right. So we hit go, and we scroll down here. We see that it's going to run 2 different models, right? It's going to run an initial model that just has the alls in there, and then it's going to run a second model that has the alls and the DIRs in there together, both predicting DTS. And so we see that in the first model, our R square is 0.15, and our R is 0.392. That's actually just a 0-order correlation, right? Should be exactly the same because it's only one predictor in our model. Move this over so everybody can see it. Can you guys all see it okay? Okay. And as far as our regression model goes, it's the same as an ANOVA model, right? We have an F of 121. It's just statistically significant. Goes up to 124. Our degrees of freedom changes from 1, where we have 1 predictor, to 2, down here where we have 2 predictors. And then we get to see, let's start with just affect lability. It is a negative relationship between affect lability and distress tolerance. And you can see we have a 0-order correlation of minus 0.392. That matches our beta perfectly. It also matches our part and partial perfectly because we only have 2 variables in that model, right? As we add a third variable to the model, a second predictor, we see some changes. Something happened to alls. It was like very significant, and it dropped way down here, right? 0 order is going to stay the same, but our part and partials are way down here. They were way up here. And our beta coefficient, minus 0.013, p-value of 0.784. What happened to alls? Yeah.
Why is it a zero thing even when we lose a significance, a zero order stays the same?
Oh, because the 0 order isn't part of the model. It's just saying, like, if you were to just look at the bivariate correlation between these two things, technically everything from here over is not part of this model. It's saying, like, if, right? So, yeah. What happened with alls here? It was suppressed, but we actually wouldn't necessarily, we could call this a suppression effect. It's not statistically significant anymore, right? There is the suppression is a special case of what? Oh, mediation is also a special case of what? Redundancy. Suppression is a special case of redundancy, right? And so what we're talking about here is that emotional instability and difficulty in regulating your emotions are redundant with each other, right? They're highly, highly related. And so, unfortunately, and you see this huge drop in the partial correlation, right? And that huge drop is saying that we had a 0-order correlation that was quite high, and that 0-order correlation drops to minus 0.011, which means that the overlap that we saw between x1 and y is almost completely gone now because we've added the multicollinearity with x2, right? We also see a 0-order correlation here that's 0.521, and it drops to 0.373. It's still pretty robust here, and that doesn't quite map onto our beta, right? But remember that this is looking at a proportion of all variance, and this is looking at the proportion of the unexplained variance, right? Makes sense? This is, yes, a special case of, or not a special case, but this is a case where you could call this suppression. I would just call it redundancy. We're going to talk about at the end, I'm going to show you another model of redundancy, and we're going to talk about how you can handle redundancy. There's ways to deal with it. Let's look at a different model that's a better kind of depiction of what suppression really is. So let's go analyze regression, linear, and let's take out DTS. Let's put in affect intensity. Let's take out DERS, and let's take out alls. We're probably going to add them back in there, but right now we won't. So for our predictors now, we had DTS as our outcome variable before. Let's put it in as an independent variable. Then let's hit next. And let's put in DERS as an independent variable. And let's hit next. And let's put in alls as an independent variable. When you do this, when you hit next, it's actually creating 3 different regression equations, right? It's going to run the regression equation with just that one predictor. Then in the next block, it's going to run that regression equation with that one predictor and the new predictor. And then in the last one, of course, it runs a regression model with all 3. Okay, shouldn't have to check statistics again, but we'll look. They're all still checked. That looks good. Let's hit go and see what happens. here are our three different models. We see that the R squared here is not is very minimal, and it grows as we add predictors to the model. So let's scroll down here. And distress tolerance, our standardized beta, minus 0.026. Remember, these should all match in at least the first model, right? So what's the relationship between distress tolerance and emotional intensity in that first step? There isn't any, right? Yeah, like there's no relationship. So if there is, it's negative, and it's not statistically significant. Next, we add difficulties in emotion regulation to this model. Difficulties in emotion regulation has a strong positive relationship, and then something weird happens. We went from a negative, non-significant relationship for DTS to, what's this?
Small correlation, but significant.
It is a positive, statistically significant relationship, right? And then we look at the last step. We have DTS and DERS and ALS, and all three of these now are positive and statistically significant relationships. What is going on with DTS?
Would this be an example of full mediation? DTS doesn't directly explain it.
It could be an example of full mediation. It's better explained by something else. So remember, when we're looking at a beta weight, we're looking at the entire y, right? And then when we're looking at the part and partial correlations, we're not looking at the entire variance of y anymore, right? We're looking at only the variance in y that's error, right? We're dividing what we can explain by what we can't. And so in this model now, our zero order correlation changed dramatically, right? Or I mean, our zero order to our partial correlation changed dramatically, and it went in a direction that it shouldn't. Remember, as I was walking you through this, I said there's a specific order that these things should go in, and this one went from, it's an absolute value of order, right? This one went from minus 0.021, and it jumped way up. And that's because so much of the variance was explained by the other two variables that the little bit of variance that could now be explained by DTS is the denominator for that is just so low, right? We've got a much, much smaller denominator, and it's just a sliver of variance, but it's that sliver of variance that has gone positive instead of negative, right? The correlation has gone positive instead of negative, and that is how we find out if something has a suppression effect, right? We see a dramatic change from the zero order to the partial correlations, and typically that's accompanied by a change in sign. And that change goes in the wrong direction, right? Like it should be getting, if you look at these, our zero order is 0.4, and then it goes to 0.23, and then it goes to 0.214. That's the order that these are supposed to fall in. And when they start falling in the wrong order, that's an indication that we might be dealing with some sort of a suppression effect. It's not a guarantee, but it's a first indication that that might be a suppression effect. So. All right, let's look at one more model here. Let's go analyze, regression, linear. Pluck all of these out. And let's add Yaktote YACTOTE is the young adult alcohol consequences questionnaire. This is the alcohol consequences that a person has experienced over the past 6 months when they've been drinking. And let's look at PBS and drinks. Oh, sorry, let's put that in the second step. Let's add drinks to the second step. So let's talk a little bit about what PBS is. PBS are behaviors like I set a limit on the number of drinks that I'm going to have when I go out. I set a time limit on the amount of time that I'll be out drinking. I alternate between alcohol and water when I'm drinking. It's behaviors that people can engage in that A, reduce the amount that you drink, and B, reduce the frequency of alcohol-related consequences that you have. Let's hit OK. And we see here, whoops, come on you. PBS are negatively associated with alcohol-related problems, right? And that is a statistically significant association. Our zero-order correlations match our betas. That's all the way that it's supposed to be. And then when we add alcohol use to this equation, though, something weird again happens. PBS, which was a statistically significant predictor of alcohol use, is no longer a statistically significant predictor. I mean, a p-value of 0.053. You know what? We'll come back to this. I want to talk about this for a second. Let's talk about p-value of 0.053. What is the difference between a p-value of 0.053 and 0.05? 0.03. It's simple math, right? You bet. In terms of scientific publications, what's the difference between 0.053 and 0.05? Yeah, right.
I would say it depends on the context.
It probably does depend on the context. There's this. I have a paper out there, and I love this paper. So in my old stats book, the stats book that I had as an undergrad, there was a discussion of 0.05 versus 0.06. And Rosnow and Rosenthal quipped in this book, but surely God loves 0.06 as much as 0.05, right? And I just love that quote. We set this level of 0.05 fairly arbitrarily, right? I mean, and really, what is 0.05? What does it mean? It's telling us the likelihood of what? Yeah, the likelihood that the data that we drew and the associations that we found happen by chance, right? By pure and that's the beautiful thing about statistics is you never have to say I'm positive. You can say like I'm certain with some error around that. And so there is a chance again, and if the data that you drew was drawn from the tail of some distribution, that's your, at that 0.05 level, or the association that you found is in a range of associations that have a mean association and then that is zero, and positive associations that range up to whatever, right? And you drew that association from the tail, at least you're saying like, hey, the probability that this came from the tail is 0.05, right? That means that the likelihood that this happened by chance is fairly low. Like we want to say it's fairly low. So we found that there's a lot of things that influence whether or not that is actually true. And in fact, small sample sizes tend to inflate the likelihood that you draw something. But if we draw something from that tail and we say that just because it says 0.05, that doesn't actually mean that the association that you found is true, right? And sometimes it isn't. And what is that called? When you get a p-value of 0.05, but the effect is not really 0.05. The effect in the real world is not 0.05. You have made what type of an error? That is a type 1 error, right? You said something was there when it really wasn't. Of course, we have the other thing, which is when the p-value is 0.06 and you say, oh, it's not there, right? And when it really is, and that is what type of error? Yeah, it's a type 2 error, right? When you said it's not there and it actually is there. So in this case, regardless of whether it's full mediation because the p-value no longer is technically 0.05 or partial mediation because at least we see this decrease, we can check and see, is this consistent with what we would think of when we think about suppression, right? The relationship between PBS and alcohol problems was negative, and it was statistically significant, and it remained negative, though no longer statistically significant. Our zero order correlation was negative. Our part and partial correlations are both still negative, and everything is moving in the direction that it should be moving, right? This is indicative of mediation. This is what we would largely expect when we're talking about testing for mediation. All right. The other piece to this is PBS use occurs before drinking, right? And so theoretically, if you start to engage in these behaviors, then you drink less, and then alcohol problems don't occur before you drink, right? They occur after you drink. Then you experience fewer alcohol-related problems. That is a theoretically sound rationale for a mediation model where PBS use leads to lower alcohol use, which leads to fewer alcohol-related problems. Though I'll tell you, even if you have a good theoretical rationale, if you collect cross-sectional data, reviewers will chew you up and spit you out. I think we've had 6 rejections in the past couple of weeks, unfortunately, on various articles. It's brutal because it's cross-sectional data, so we have some cross-sectional data. They don't like it. All right. Hopefully the reviewer watches my video and knows that I'm complaining about them. Let's move on to so just out of curiosity, before we move on, any questions about looking at suppression and looking at mediation or testing for mediation? If we're doing the Barron and Kenny method, I know I said any questions and I immediately started talking. If we're doing the Barron and Kenny method, then what we really want to do, let's test this using the Barron and Kenny method. So we're going to go analyze, regression, linear, and so let's just pluck all of these out to start with. The first thing that we want to do is look at the relationship between drinks and yak tote, right? Oh, I'm sorry, not drinks, PBS. PBS and yak tote. The next thing that we want to look at is the relationship between, I mean, you can kind of go in either order here, but oh, can I do that in a block design? No. All right, so we'll just run this one. There's our first one. We'll come back to these. Analyze, regression. What's the next thing that we want to know? Say it again. Oh, yeah, just PBS. Just PBS in the first one. Then we want to know, are drinks related to yak tote, right? Just drinks. We hit go. Analyze, regression. Now we want to know what? PBS related to drinks. Put drinks up here. PBS here. We hit go. And then analyze, regression, linear. And what's the last thing we want to know? Yep, you're right. We want to know what happens to PBS when we have drinks in the model. So if we're doing our Barron and Kenny steps, step 1 is PBS related to, oh shoot. Oh, it's all the way at the bottom. It's about to say, man, I must have done something really wrong. Okay, is PBS related to alcohol-related problems? It's negative, it's statistically significant. The answer is yes. Next, we want to know, are drinks related to alcohol-related problems? It is positive, it's statistically significant. The answer is yes. What's the third thing that we wanted to know? Are PBS related to drinks, right? And we see here that PBS are inversely related to drinks, right? Statistically significant. And then in our final model, we see PBS is no longer statistically associated with alcohol problems, but drinks is statistically associated with alcohol problems. So the indirect relationship, the indirect effect of PBS on alcohol problems is what? What is our indirect effect? Remember, I showed you this on the board. It's still up there. How do we calculate the indirect effect?
The data weights between PBS and drinks on, to multiply those two together and
Yes.
divide it by the asymptotic.
Yep, so if we just multiply those together, then we have the actual coefficient for that indirect effect, right? Where's my calculator? Here we go. Let's do this. So we're gonna multiply the unstandardized coefficient 5.388 times, and should our indirect effect between PBS and alcohol problems be positive or negative? Negative, right? Negative 0.157 times, I couldn't figure out how to make it negative on my phone. 5.388. The indirect effect is a minus 0.845916, right? We don't know if that's a statistically significant indirect effect or not, but that is the actual value of the indirect effect, right? That is the slope coefficient for the indirect effect. The way that we test that indirect effect is going to be saved for another day. Because there's a lot of different ways you can actually test it, and one of those is to use a bootstrapping approach, and we will go through that. I'm teetering on whether or not I should teach you guys how to use process or not. Who's used process before? Do you guys know what I'm talking about? A few of you. None of you guys. IO folks, you guys don't use process? Good. So what process is? It's really great in that it's a program a program that was written by Steve Hayes to do all different types of moderation and mediation analyses. And then he will lay out, like, here's model, and like there are literally hundreds of these models, right? And he'll be like, here's model 77, and he'll lay out how you run model 77. Here's the problem. I see this all the time where people will post in these groups that I'm in, where they're like, I'm running model 77. Like, they assume that everybody understands like process and what's going on. But I'm running model 77 and I don't know how to interpret the results. And it's because they were never taught how to just do this without using model 77 or model whatever, right? Like, I feel like process has opened up a whole world of new modeling techniques to people using SPSS. And they're standing on the heads of the people that came before them and not understanding what they're actually doing. If you really understand moderation and mediation, you don't need to use process. You can just do it yourself, right? Like, you can go in, calculate your variables, run your models the way that you want to. It's nice to draw them out so that you know exactly what you're getting, right? But it's also like process, I think, just dumbs down things and leads people to make mistakes in how they're modeling. So I don't like to teach process, but process will give you all of this stuff rather than having to compute these things on your own. If we do, let's check something out though real quick here. Analyze, regression, linear. I'm wondering if I can get, yeah. So if you check covariance matrix right here, then you can actually get right here these are the covariances. Nah, that's not what I wanted it to be. Those are the covariances and correlations of the variables. Oh yeah, no, it is. I'm sorry. And so these are the this is drinks predicting yak and drinks predicting, or I mean, drinks and PBS. And so this is the covariance of the drinks mean, right? Like this is your mean covariance for drinks. This is the shared variance between, is that right? That can't be right. No, that's not how you get them. Analyze, let me look again. We might have to Google how to get the asymptotic covariances here because it should be right. I'll have to double check on that and get back to you. I'm not sure that that's right. In Stata, it's easy because you just request the matrix. But anyway, yes, you can get the covariance, the two different variances of those slopes, and then you just calculate a pooled variance of them, divide it by that whatever value we had, and that will give you a z-score and tell you whether or not the indirect effect is statistically significant. All right, let's do one more thing. Let's open up the other data sets. Oops. So for Amy and Gabby, this might be interesting for you all, because this is data from Mike's lab. This was a paper that I worked on with Mike, and so Mike Dunn, a lot of the research that he does is alcohol expectancies. You guys know what alcohol expectancies are? It's the whole reason that we have this room. Actually, it's because when people drink, they expect to feel a certain way or have, they expect alcohol to have certain effects on them. And so here we have four kind of basic alcohol expectancies. We have social, tension reduction, liquid courage, and sexuality. And then we have BAC. So social is you expect alcohol to make you feel more social when you're drinking. Tension reduction, you expect alcohol to reduce your stress and anxiety. Liquid courage is you expect alcohol to make you braver, more courageous, more confident. I think confident is the word that they like to use. Sexuality is you expect alcohol to make you more sexual, I guess. So anyway, let's do a model. Let's do this. Let's go. Does everybody have this data pulled up? Are we good? All right. Analyze, regression, linear. We're going to predict BAC, and let's go social, next, tension reduction, next. Let's do sexuality, and then next, and then let's put liquid courage last. So these are college student drinkers, social, tension reduction, liquid courage, sexuality. What do you think is going to be the best predictor of their BAC? Okay, so we have a tension reduction. Liquid courage. Is that why you drink, Matt?
Yeah.
So let's find out why Matt drinks.
I would like to.
All right, we hit go. Here's our output. And so in our first model, just social. Social is a pretty good predictor, right? Statistically significant, our p-value is 0.03. Standardized beta is 0.216. When we add tension reduction to that model, tension reduction is not a good predictor at all. Sorry, Ardis. Tension reduction is a bad predictor amongst college student drinkers. Guess who it's a really good predictor amongst? Possibly.
Theoretically.
People with alcohol use disorders, actually, right? Because many of them have had a lot of experience where alcohol is reduced. And in fact, tension reduction is usually a poor predictor of use, of how much you're going to drink. It's a great predictor of how many problems you're going to have, because it signifies that reinforcing effect, negative reinforcing effect that you're getting from alcohol. Not that that has anything to do with the class today, but just FYI, tension reduction is not usually a reason to drink. It's a reason to reduce anxiety and stress, and consequently it leads to problems. All right. We put sexuality in there, and when we put sexuality in there, tension reduction goes to a negative coefficient, still not statistically significant. What do we call that? It's actually not suppression. It's probably just nothing. I mean, it wasn't significant. I know. It wasn't significant in the first place, right? And if you look at those part and partial correlations, they seem to be going in the direction that they should be going. So I wouldn't actually call this suppression. I would just say tension reduction doesn't matter. And if it's positive and non-significant or negative and non-significant, then it's still non-significant, right? It just isn't related. All right. And then we get down to the last one. But in here, social social is not predicting. Actually, nothing is predicting here, right? Isn't that weird? All of these things, the p-values have gone to 0. And then when we add liquid courage in, liquid courage is 0.053, but that's also not statistically significant. We just had a party with 0.053 and figured out, right, that it's not really statistically significant. Now, when we look at our part and partial correlations, are they doing what they're supposed to be doing? I mean, they're all getting less, right? They flipped signs here, which is kind of weird, but they're all decreasing the way that they're supposed to be decreasing, which means that we're not thinking about suppression here, right? We're thinking about something else. And I said suppression is a special case of what? Redundancy. And that's exactly what this is. We have a whole bunch of redundant variables that all have zero-order correlations with drinking that are reasonable, right? And with the exception of maybe tension reduction, probably all statistically significant. But they all reduce to basically nothing over here, with the exception of liquid courage, which is still, it's pretty weak. So what do we make of that? What do we do if we have something like this? What would you do if your data set, you collected data and you had these 4 predictors, you put them in this model, and each one of those predictors independently is statistically significant and predicts your outcome. But when you put them all in together, everything falls apart. What's that? Get a drink? What's that? Okay, you can combine them. That's one option. Yeah, so I suppose there's 3 different options, right? The first option is you can combine them into a single variable. Getting a drink, that's the 4th option. Another option is you could just run a bunch of independent regressions, right? So you've got 4 independent regressions. What's the problem with that? What? Say it louder. Inflates what error? It inflates your type 1 error, right? It inflates the likelihood that you're going to find something statistically significant. What can you do to correct for that? What's that? Yeah, you can do some sort of a pairwise correction. And so in this case, with 4 predictors, what would your pairwise correction be? Your new threshold for a cutoff for P would be what? 0.0125 probably, right? You just divide 0.05 by 4. So you could do pairwise. You could just leave it as is and say none of these things are none of these are significant predictors, and I think that happens quite frequently. And then the last option that somebody said is you could make one single variable. So how do we do that? Two ways, really. No, no take. Anybody here a Ricky Gervais fan? He does this skit about how the first person contracted the AIDS virus, and he was talking to his doctor. He said, "How did that happen?" And Ricky Gervais goes, "One of two ways, really." And then he walks through these two. It's funny. I love Ricky Gervais, by the way. I do this, right? I get sidetracked. Who watched Ricky Gervais's monologue and then his like incessant roasts one after the other on the Golden Globes? Oh God, it was uncomfortable to watch, but so funny.
Tom Hanks' reaction.
Yeah, I mean, wow. It's something. It's brutal. I mean, I felt so sorry for the people in that room. I laughed so hard. But the people in that room, I don't think any of them were thinking it was all that funny, except Adam Driver. Adam Driver was a Marine infantry guy, and so he's got a pretty sick sense of humor, I think. I played trivia with a couple of veterans, and the whole reason is because, yeah, this interesting guys. All right. Let's do this. You can do one of two things. You can do one of a bunch of different things. One way that I like to one of the ways that I like to do this is just combine these into an average, right? So we can take the average of all of these things. We can also use these to make a latent variable. And so in the video for this week, I think it was in the video for this week, didn't I show a latent variable of alcohol expectancies? It's from a paper that I wrote with Mike. But all right, if we're just doing straight regression analysis, let's go like this. Let's go transform, compute. Let's call it expectancy. Let's just call it expect. I don't like long words. Expect equals, I think we can just do mean, might be average, social, comma, tension reduction, comma, liquid courage, comma, sexuality. I think that's right. I think that's all we have to do. Let's try it. Looks like it might have worked. Expect, right there. All right, so now we can go analyze, regression, linear, and let's remove all of these. And let's just put in average expectancies. And we hit go, and we see that expectancies, more positive expectancies, are positively associated with the amount that you drink. And pretty significantly, this is a sample of like 100 people or something, right? So it's a smaller sample, and we see a pretty strong relationship between alcohol expectancies and alcohol consumption. So, again, it should match perfectly our zero order correlations, right? And our partial and parts should also match that, because it's what type of model? A simple bivariate, right? What would happen if we added all of these other expectancies back in there? What do you guys think? What'd you say, RDs? Yeah. And, oh wait. Oh yeah. And it won't run with expectancy because it is perfectly correlated with the overlapping variance of these, right? It is the mean of all of those, so the overlapping variance is perfect. If you run this in Stata, it will just give you zeros for all of this. Are you using Stata, Angie, or are you using SPSS? I don't blame you. I mean, it's easier to follow along with. Yeah. All right. Any questions?
When you're computing your average variable, that only works if they're on the
Same
response
scale. Yeah. What do you do if your variables are not on the same response scale?
You have to, so let's say you have a 7-point scale and a 5-point scale, you have to transform 7 point to a 5 point, or
Oh my goodness. I don't know if you could do that, could you? How do you set things to be on the exact same scale? Yeah, you can actually, you could transform every one of these into a z-score, and then you can do the mean of that. And if you make all of these z-scores, um, interestingly, the beta coefficient and the unstandardized slope become the exact same thing, right? Because now you have a standardized variable. Yep.
So if you were reporting this and you say like the expectancy like had a significant effect, you would know which of the actual variables it was though.
Yeah, you know what I would do? So what I would say is we examined a model that we examined 4 independent models or the covariance or correlations between all of these expectancies and alcohol consumption, and we found significant positive correlations between all expectancies and alcohol consumption. Next, we conducted a regression model where we entered all expectancies into the model simultaneously, and we saw that none of the expectancies were statistically significant predictors of alcohol use, and a dramatic reduction. You can't say a significant reduction, but a dramatic reduction from the zero order correlations to the part and partial correlations. You don't have to list them, I would just say that. Thus, we assumed that these expectancies were redundant and consequently formed a mean variable of all expectancies. When you do something like that, you also want to examine when we combine a bunch of variables together, we want to know if they really are holding together well, right? And what is a way that we can test whether or not these variables are holding together well? Well, so we've made we've made one variable out of 4, right? And we want to be able to say that we're justified in making that variable, that these things have that they are, I'm going to say this word and then it's going to be obvious, that they're internally consistent, right, with each other. And so we have a measure of internal consistency or internal validity, and that measure is what? Cronbach's alpha, right? So you can calculate a Cronbach's alpha. Anybody know how to get Cronbach's alpha in SPSS? How do we do it? Where do we go? Because I don't know. I know how to do it in Stata. It's easy. You just type alpha, and then you say the numbers and hit enter.
Analyze, scale,
Oh, yes.
and then reliability analysis.
This is making sense. So we can grab these, throw them over, and scale the label. Let's go expect to or something. And do we need any of that stuff? I don't think so.
Usually the scale if I deleted is nice, but that's also important.
Okay, let's have a look. And there it is, Cronbach's alpha 0.85. What is a good, what are our ranges for Cronbach's alpha? What are our acceptable ranges for Cronbach's alpha? Yeah, so 0.8 and up is good, right? 0.9 and up is excellent. 0.7 and up is acceptable. 0.6 and up is what you say when you've got another rationale for why they should be together and they're not. Which happens a lot with the audit, FYI. I mean, the audit oftentimes, if you break the audit into its 3 scales, then it has good internal consistency within scales. But in our recent paper, I think, because we just used the audit C for something, I don't remember what it was, there are some other measures of internal consistency that are tooled specifically for like fewer items. So yeah, I can't remember what we used in that paper, but we didn't use Cronbach's alpha. I used something else. But anyway, any other questions? No? All right, that is it. I will try and get these videos up. Your homework is ready. There actually isn't homework next week, so we don't have to worry about that. We're just going to be doing data visualization. So there's a video that you guys can watch, and then when you come in, we will just play around with looking at our data and how we. It's the first step in data cleaning, which we haven't talked about yet, right? But data cleaning is an important piece, and we're going to spend a lot of time talking about data cleaning in this class too. But all right, that is it. Have a good day and an even better weekend. Go see a movie.
Oh, okay.